We will be starting soon. Hold tight. We'll be starting in about 5 minutes. Sending out the links so others can join this live stream. We'll be starting in just a few more minutes. Make sure you have questions ready. I am monitoring the chat, and you can also message me inside of Canvas. We're getting started, guys. Welcome. Welcome, everybody. All right. Just getting set up here. I've had a lot of questions come in about Chapter 8, Chapter 9. There were some questions about 7. I really want to get to those questions. I see one question from 5.3. And I'm thinking maybe we should start there, and then we'll jump 5. Let's see. Question for section 5.3, problem 14 or something like that. It's kind of a thing from the past, to be honest, because chapter 5 is not going to be on the test, and chapter 5, we're just not going to be doing it anymore. But I do know that some of you guys are going to be doing your homework. So I want you to improve your homework, and one way to improve your homework is going back over old problems from the past. Now, let me see which one it is. The person said 5.4 or 5.3, so I'm not sure which one we're talking about, but let me check it out anyway. It could be 5.3 or it could be 5.4. I know this has to do with the binomial probability distribution formula, and you can actually do this on the calculator. Let's see what it says. A certain television show recently had a share of 75, meaning that among the TV sets in use, 75% were tuned to that show. Assume that an advertiser wants to verify that 75% share value by conducting its own survey, and a pilot survey begins with 13 households having TV sets in use at the same time of the TV show broadcast. So the first question is, find the probability that all of the TV shows, that all the households, which is 13, are tuned to the TV show. All right. Again, this is a probability distribution function problem, and there's a lot of ways to do these kind of problems. You can't just take it straight forward and say, oh, the probability is 75. You can't necessarily do that because there's different combinations of 13 households. And so we have to account for all of the different combinations as well. Let's see, let me get my pen there. So what I'll say is, we know that the n of the sample is 13 and our probability is 0.75. And we're trying to find the probability of, say, all 13 is being tuned in. All right. So what is that probability going to be? But you got to keep in mind something. The probability distribution function is a very complicated function. It's NCR, and then probability of x to the n. Actually, we'll use P and Q. And then the Q to the n minus r power. And so once you've done this, then you'll be able to get the answer. But what we'll do is look at how we can actually do this on the calculator, because I think that's where we're headed. You have to know how to be able to do this kind of problem on the calculator, so let's do that. We're going to have to use a binomial distribution formula. So we go into second, distribute, and go down to our probability distribution function. Now, there's two different ones. There's the binomial PDF and the binomial CDF. And for the probability of getting exactly 13, we're going to have to use the binomial PDF when x is exactly 13. So we'll go to A. My trials is 13. My x value is 0.75. And my probability is 0.75 and my x value is 13 as well, because that's exactly how many we want out of the number of trials. Paste it to my home screen. The first is, again, your trials, your probability, and then the x value, how many out of 13. Exactly how many out of 13. We want exactly 13 out of the 13. So we hit enter, and there it is. We got a probability of 0.023 something. Let's check that. Hold on, let's see here. More people want to come to the stream, so I'm just sending out links. Let's make sure. I'm watching your live, but will this be recorded? Yes, the live stream will be recorded. The link will be shared out as well. So let's see. Let's get back to our problem. They wanted us to round to 3 places. So let's see. It should be 0, 2, 4. I think, okay, we got it right, but the thing is, man, why is that probability so low? And the truth is because there's 75%, there should be about 75% of those households. So to get it to where all 13 are watching it, when that particular TV show has exactly 75, that's rare. The probability is less than 5%, and anything less than 5% is rare. Now the question is find the probability that exactly 12 of the 13 are tuned to the show. So that's going to be, again, another binomial distribution problem, but we're going to modify our last answer. Instead of having an x of 13, we're having an x of 12. Our probability just shot up to 0.103. Okay? Find the probability that at least 12 households are tuned to the show. At least meaning 12 or more. And that's really just the probability of 12 plus the probability of 13. We've already done that in parts A and B. So what I can do is take the sum of those two responses. Let's go. 1, 2. What's left? 7. 0.127 is fantastic. And that's how you do the problem, folks. That was the question. That was the answer. Okay, we went straight into it. I didn't want to get too deep into the binomial theorem. It's a beautiful formula. All right, it's Pascal's triangle and binomial for the FOIL method from algebra. I mean, we could get into all of that. The coefficients of the combinations of each term in the binomial expansion. And we just did a snippet of it. And it turns out that the probability distribution forms a certain type of distribution. It's very deep. It's very deep. But it is based on algebra. We're gonna jump more into the things that I really wanted to get into. I really wanted to talk about 8.2, and we're gonna jump right into the middle of it, right of the thick of it, where it starts to get tough. Okay. So let's jump into 8.2, and I will tell you this: a hypothesis test is the most powerful statistical test there is. It is extremely powerful, and the reason why is because of the evidence of the results. If we get a conclusive result, it is final. It is as good as factual, because it has to be highly significant. It stands up in the court of law whenever they're talking about certain warrant rejections of results and statistics, DNA tests, and forensic tests. They're all hypothesis tests. You can catch people lying if you conduct a hypothesis test, and I can get into how one could do that. In fact, I'll start with a little example right now. And here's an example of how to conduct a hypothesis test. And let's just say David, who is a decent basketball player, brags to his friend and says, "Hey, did you know that I'm an 85% free throw shooter in basketball?" That's David's claim. His friend says, let me set this up right. His friend says, he says, "Wow, that's actually pretty good." His friend is really a statistician and has his doubts about the claim. In other words, the friend doesn't really believe him. I mean, the friend believes him, but the truth is you can't just go around making claims like that. There has to be a way of testing this out. And because the friend is a statistician, the friend knows exactly what to do. The friend knows how to test this claim. So what the friend is going to do is say, "Hey, the friend wants to collect a sample. Say, hey, all you got to do is shoot 20 free throws for me." David responds, "Sure." Result. David makes 15 out of the 20. Friend. Actually, David, I don't believe that you are a 85% free throw shooter anymore. You lied. Now, how could this be? How could the friend, just off a simple sample, determine whether or not his original claim is true or not? Well, there is a way to do it by conducting a hypothesis test. All right, and that's how it's done, and that's how we're going to do this. And so let's jump into how one goes about a hypothesis test. And what we can do is first create the null and the alternative. And the null is that David is exactly an 85% free throw shooter. That is his proportion. It'll be a little higher or a little lower, but on average, this is his overall average. Now, the alternative, because we don't really believe him, and 85% is actually really high, it's nearly professional level, we think the alternative is that it's less than 0.85. This is actually going to be a left tail test. Now, we actually conducted a sample, and the sample was 75% because, 15 out of the 20 is 75%. That's actually, that's pretty low. Because if you're truly an 85% free throw shooter, you have no business shooting 75%. And if you keep shooting more and more, you're not going to get nowhere close to 85%. You're probably going to have to hit the next 50 baskets in a row to get your average back up to its normal par. Do you know how hard it's going to be to shoot 50 baskets in a row and make them? I'm going to explain how this works. And what we'll do is we'll conduct it on the calculator from here. We have all of the information that we need. The sample size is 20. The ones that he made was 15. And we have the probability of null. And we also have the sample probability of 0.75, which can be gathered from this because our point estimator is x over n. So we have enough information to actually go on about this. So let's pull out that calculator now. And I'm getting a lot of questions right now, so I'm not able to get deeper. But let's jump into this now. We're going to conduct a statistical test, so I'm going to click in Stat and then Test. And then what we're going to do is use a one-prop z-test because we're dealing with the proportion of how many they've made. It's not the average. So let's get into that and let's see, what do we have? Well, all we need is the p-null, which is 0.85. the successes out of the trials, 15 out of the 20. And then the alternative is that we believe he's less than. We're going to conduct a left-tailed test. So if it's less than null, if the sample is going to be less than null, that's left-tailed test. If it's greater than the null, that's right-tailed test. And if we think that it's not equal to 85, it could be greater, it could be lower. That's a two-tailed test. Double the p-value. We'll look at that. But we're going to say a left-tailed test. Then the next thing they're going to do is calculate the test statistic. Okay. We calculate the test statistic is actually negative 1.25. And then the p-value is 0.10. Interesting. The p-value is 0.10. So I'm going to write this information down. Our test statistic is negative 1.25. We knew it was going to be negative because it's a left-tailed test. And our p-value is 0.0105. Now, what do all these numbers mean? Remember that the test statistic, we also sometimes call it the Z. We get that by doing, I believe the formula for that, we don't need a formula because we have the calculator, but I believe the formula is Z, and then we do p hat minus p divided by the square root of, say, pq all over n, or something like that. You do this, and then you get the test statistic. And then where does the p-value come from? Well, if we have the normal distribution, the standard normal distribution, where the mean is 0 and every deviation is 1, then our test statistic falls right about here. And therefore, let's get some highlighters out here. Therefore, the p-value is that. And what I'll do is show you that. Oh. The shaded region represents the p-value. And so what we could figure this out because this is a 6.2 kind of question. We could do normal CDF of negative infinity to negative 1.2 and get the p-value. Because that's what the p-value comes from, okay? And in fact, I can demonstrate that as well really quickly so that we can come full circle in our understanding. Because they're going to probably test our knowledge on this. So number 2, negative 1, that's the lower bound, and then our upper bound was negative 1.25. And that's it. Our mean and our deviation is 0 and 1. We hit enter. Let's go back in there. It says it's some kind of okay, so we need a negative symbol, 1.25. And then we're going to paste that to the home screen, hit enter, and we got the p-value. And now the question is, now we never really said what our what our alpha is, significance level. Usually it's about 0.05. And an alpha level of 0.05, like the shaded region is 0.10. That's how much area it takes up. Half of that is 0.05. This is more of the once once the p-value, or the area to the left or right of our test statistic, falls in this region, is lower than our alpha, then we get a conclusive result. We can reject the null. So let me summarize that. If the p-value is less than alpha, and sometimes we set alpha to be different things, and but in this course we don't play around too much with this. We don't go deeper into what kind of errors we'll get by changing our alpha that much, and then how can we control that by calculating the power of a test. But what we're looking at right now is this: that if the p-value is less than alpha, then we can conclude that I shouldn't say conclude that, but I'll just say we can conclude, or I'll just say it even though it's broken. The null, I'll say the alternative is true, and we reject the null. So this is we get a conclusive result whenever the p-value is less than alpha. And I'm going to get back onto OneNote because we have a little bit more space, and I'm going to share with you guys about the different results again, because this is very important. Remember now, we had a standard normal distribution with 0, and let's just say for the sake of argument this is 1.25. It's not drawn to scale. And I'm going to shade this region in again. And what I'm going to say is that the p-value of the green region we said was 0.10, but we set our alpha, and this is where it needs a different color. They're overlapping each other, because remember the green goes from here all the way down. And this part, I'm going to call this little c, because that stands for the critical value. And here's our alpha, which is 0.05. Now, what's the critical value? Well, we can find that by using inverse norm. All right, let me get into inverse norm for a second. Second, distribute number 3, and then we're going to do 0.05. The lower left tell, negative 1.6. Sometimes we just say 0.65, or you can just keep it at 0.64. So negative 1.64. This is our critical value, the CV, and this guy is our test statistic. Now this is very important. In order to conclude after a hypothesis test, this is the key point right here. And hopefully I clarify a lot of misunderstandings and we get it solid. And I'll rewrite what I did before. If the p-value is less than alpha, we reject null and accept the alternative hypothesis. But guess what? That's the same as if the test, that's the same as if the test statistic is less than the critical value. That's the same as this piece is less than this piece. We reject the null. And in our case, it didn't happen. David's basketball problem, it didn't happen. So maybe the friend should actually believe David. We can't reject David's claim based on that sample. He could very well be what he claims to be, an 85% free throw shooter. We do not have enough evidence to reject him. So we don't have enough evidence to claim that he's a liar. That was too premature. He had to have shot even worse. All right, he probably can come back and make the next 40 or 50 shots. Maybe that sample was a little off, but let's get into that as well. So what happened was, what about when the p-value is greater than the alpha? We come down some, and this was in David's case, literally. The test is inconclusive. We cannot reject the null. We can't accept the null either. Just note to self, not enough evidence. So basically, the test falls apart. And that's exactly what we saw, because that p-value, and let's look at it. How do we know that? The p-value was 10. And our alpha, we set our alpha, which by default, see if we can keep scrolling down so many more space there, right? By default, the alpha is usually 0.05, unless otherwise stated. All right, this is a good alpha level. Sometimes it can be even lower where we want to be certain. We want a p-value to be small. Now I could have set my alpha to be 0.15, and then, hey, p-value would have been less than alpha. But the truth is that's not a good idea. Okay, we can likely get an error. We could end up rejecting the null and accepting the alternative, and in actuality, the alternative could have been false. That's the gist of a hypothesis test. I think we should look at some problems to get a feel for the different contexts and the different situations. So let's do that, and then we'll even look at some from chapter 9 as well. All right, guys. What we're going to do now is look at some problems from chapter 8. And let's jump into some that we don't have to go all the way back. I mean, we could do some from let's say problem number 8 or something like that, or problem number 9. The claim, let's see, the claim is that the IQ scores of statistical professors are normally distributed with a mean greater than 115. All right, so we're dealing with a mean and not a proportion this time. So that's a different type of test. We mostly talked about conducting a hypothesis test on a proportion. So they kind of threw a curveball at us this time, because they're giving us the mean, and the mean is greater than 115. A sample of 14 professors had a mean IQ score of 116 with a standard deviation of 3. So when we have to find the test statistic, it's a different kind of formula. But our calculator can handle this, all right? It's just not going to be a one-prop z-test anymore. It's actually going to be just a regular t-test. So stat, and we go over to test, and then I'll go to number 1, one-prop z-test, and we have the statistics. And what we'll do is enter in the data. It doesn't matter what we enter in for the null, because we just want the test statistic. But anyway, I will put it in. We're gonna say that because they're testing that the mean is greater than 115, let's assume that it is 115. The standard deviation is 3. The mean is given at 116. The mean is a little greater. And then the sample, we sampled 14. I'll set the null hypothesis to be greater than that, which is good. And now calculate. Well, it looks like I got the test statistic is 1.24. My p-value is 0.89, And then also the mean is 116, which we knew. So the test statistic, they want us to round it to 3 places. That's 1.247. And that was it. You won't see too many with the mean. Most in this section, I don't. This is probably even out of place. Most in this section is about the proportion. Let's do some more. And I can even show you how one could do this using the table. Like for example, the p-value. I could get the p-value just if I didn't have a calculator. I could use this because I know the p-value is going to be to the right. So let's look at what do I mean by that. Let me write down the information that we have. Our alpha is going to be 0.01. We might not need that. I don't know. Depends on the question. The test statistic is positive. And then here's the information that we really needed. The P for the alternative is 0. Let me double check that. 0.3. That lets me know what kind of test it is. So this implies a right tell. Which means in my standard normal distribution, my test statistic is going to be 1.75. So to get the p-value, that yellow region will be the p-value. But here's where it gets weird. Because my alpha is 0.01, and let's say I don't want to overlap them, so I'll just put it underneath. That's sometimes they do that, okay? It's like thinking in another dimension, kind of. But imagine they're overlapping each other. But just for clarity's sake, my alpha, in order for the test to pass, the p-value has to be less than alpha. I'll just estimate it to be here. And what is this value? That's some critical value. Now the alpha is 0.01. So I actually can find the critical value. And you know what? We could tell right away. We could tell right away. Let's get the p-value here. And then let's get the critical value here. So in order to get the p-value, this normal CDF, in order to get the critical value, it's going to be inverse norm. Inverse norm. All right. Let's get the p-value. My lower bound is 1.75. My upper bound is going to be a very large number. So we go to second distribute. We go to the normal CDF number 2. And we go into my test statistic is 1.75. And then I'm just going to put in a very large number. And hit paste. .0427. That's not bad, but it's not lower than alpha. So right away we can say, hey, we cannot reject the null. We have no, we don't have sufficient evidence to warrant a rejection of the claim, or the null as the claim. And we cannot accept the alternative as the claim because the p-value is not less than alpha. So that's by comparing these two. But what if we wanted to compare the test statistic with the critical value? We can do that as well. Let's find the critical value. Well, I know the area to the right is 0.01, so I'm going to do inverse norm. And then I'm going to do, well, the area to the right is 0.01, so the area to the left would be 0.99. .32. And now, guess what? The critical value is greater than the test statistic. Which means you cannot, again, we have to, there's no conclusion. In order, again, the test statistic has to be less than. So there's two different tests there. Okay, it's a way of comparing them. Let's answer the questions. What was the p-value? Well, we got the p-value to be 0.0. They want 4 places. 0.427. Well, they said the critical value is 1.75, and I put in, I think I put in 1.72. Okay, so let's put in 1.75 is really important. That's a big difference. So we're getting 0.0401. 0.0401. What are the critical values? There's only one because there's a right-tail test. We figured it out. It was 2.3 something. 2.32, and I think they want 2 places, of course. But I should round it to 2.33. That was it for that. Okay, I see the chat is getting pretty long, so let's jump to 9. I'll just look through some and we'll jump to where they get good. Well, they give you all this stuff here. Look at your alpha is 0.05 and your p-value is 0.73. Or your p-value is 0.009. Not sure which one to do. Maybe this one. Let's understand this one. I like tennis. So since an instant replay system for tennis was introduced at major tournaments, men challenged 1,413 referee calls, with the result that 427 of the calls were overturned. Women challenged 777 referee calls, and 228 of the calls were overturned. use a zero point 0.01 significance level to test the claim that men and women have equal success in challenges. That is a clue or a hint in saying if the claim is that they're equal, the alternative must mean that they're not equal. And another reason why I'm going to choose this one is because the null should always be set equal. So we can actually reject quite a bit of them. And then I'm going to go with not equal to because they said they want us to test a claim that they are equal. And the only other negation of that would be not equal to. And I should say that if P1 and P2 is the same, that means the difference of them is 0. And what we mean by that is, and I'll take, sometimes you'll see these tests set up like this. Well, we see it set up like this, but sometimes it's written like this. They mean the same thing. So if two things are equal, that basically means that their difference of them is 0 as well. Let's check. And now, how do you calculate the test statistic? Well, it's just some formula. Okay? But we use technology in our class. So let's use that. We're going to find a test, and we're dealing with a 2-prop z-test. And x1, I guess we'll let x1 be the men because they were introduced first. And it's the successes, so 427 out of 1413. And then the women, they got 228 successes out of 777. Crap. Oh, let's get back in there. And we're going to say that the sample size of the second population is 777. And the alternative is that it is not equal to P2. They're not equal. That's what we want to know. Do the men complain more, or do the women complain more, or is there no difference, no significant difference between them? Well, that p-value is not significant. It's not less than 0.01. The test statistic is 0.42, but the p-value is 0.66. So first let's enter in the test statistic, 0.43. My p-value is 0.6685. Alright, I thought I was going to have to round that. Alright, that's fine. And now it's time to answer the question. Because the p-value is not less than the significance level, so it's, in other words, it's greater, so we fail to reject the null. We can't reject the null. And then we can say that there is not significant evidence to warrant a rejection that the claim that women and men have equal success in challenging calls. I actually feel like they did not word that properly, to be honest with you. Um, they should have said, and this does happen. But I just want to get into it. But if you do run into some wording issues, let me know. I will delete those types of problems from the test. But yeah, they're all just, going to be a 2-prop z-test in this section. And I think 9.3 is probably going to be when we're dealing with two different means. So just read through the problem carefully. Take out the information that you need. Here's another one. Um, let's look at this one, and then we'll probably wrap it up here and regroup and come back again, maybe sometime this weekend. But another problem says, in a random sample of males, it was found that 21 write with their left hands and 208 do not. In a random sample of females, it was found that 70 write with their left hands and 453 do not. Now keep in mind, they asked more women than they did men. Use a 0.01 significance level to test the claim that the rate of left-handedness among males is less than that among females. So I'm looking for, my first group will be males, and the second group, the second proportion will be females. And because they said test the claim that the rate of left-handedness among males is less, I'm going to go with C. See, the null should always be equal, and then the alternative cannot be equal, but more of an inequality. And now identify the test statistic. That is a matter of just using the formula to do the test statistic. And for us, we don't need the formula because we have our calculator. And so what we're going to do is go right back in there. We go into stat, we go into test, and we go into 2-prop z-test of 6 for my calculator. Enter in the data, 21 and 208. And let's enter in this data 70 and 453. And we're going to say that the min is less than P2. And now calc. Okay, now one thing I wanted to show you was that look at the proportion of P1 and the proportion of P2. We converted them to proportions to compare. Even though they didn't have the right sample size, like even though we did more women than men, when we convert them or calculate the proportion of left-handed to non-left-handed, now we can compare P1 and P2. And we see that P1 is less. But is it so less that we can state statistically that it is significantly less? That men, can we then conclude that there are more left-hand women than there are men that are left-handed from this test? And we cannot, because with an alpha of 0.01 and we have a p-value of 0.03, our p-value is not less than alpha. Now, if the p-value was less than alpha, then yes, we can conclude it as a fact. We could say there's more left-hand women than there are left-hand men. A statistical fact, I should say. We can't, not at that alpha level that we set. at 0.01. And this is a good alpha level because in order for you to conclude something of this magnitude, because the repercussions of this could be pretty significant in society if it was found out that it is true that there are more left-hand women than there are men that are left-handed. If that fact becomes a statistical fact, then wouldn't that mean that they are now entitled to certain things by law? So let's finish off the question. If I round it off, I'm going to get negative 1.86. They want two places, and it looks like let's double check what I entered in. Seems like I could have entered in something wrong. Let's see, for the men we did 21 right with their left hand, 208 do not. Okay, it looks like I've entered everything in properly. 201, 70, 453, 208. Oh, wait. Okay. Oh, no, they got me. Yeah. We need the total number of people surveyed. So it's actually the 21 plus the 208. That's actually going to be, when you take the sum of that, 229. And then when you take the sum of the other one, it's 523. And now, again, how many people were surveyed in the second sample? 523. How many people were surveyed in the first sample? 229. And then we calculate. And now I'm getting negative 1.63. Much different. What is the p-value? Is it less than alpha? No, it's actually not even less than 0.05. So it's 0.0515, or rounding to three places, 0.051. What is the conclusion based on the hypothesis test? The p-value is less than alpha. And actually, the p-value is greater than this alpha. The alpha is pretty low. So we gotta reject it. We cannot reject it. We fail to reject. This, in other words, the test is inconclusive. They could very well be the same. They could very well be the same, in other words. We can't say that they're not equal, that there's less men out there that are left-handed. We cannot say that. So there is not sufficient evidence to support the claim that of left-handedness among males is less than that among females. Okay? We got it. And if they wanted us to conduct a confidence interval, our calculator can do that as well. We simply go into stat and go back to test, and it's going to be a 2-prop Z interval test. B. The data is already in, and they want a 98%, and I have 98% set up in there already. And there's my confidence interval. And notice 0 is contained in the confidence interval, which means that the difference could very well be 0, which means that the null could be true. But a hypothesis test is not testing the null. It's testing whether or not the null holds up, which is the assumption. So let's put in this, and they want 3 places, so I'm going to round that off to 3 places. Negative 0.98, and then also 0.012. 4. What is the conclusion based on the confidence interval? Because the confidence interval limits does include 0, it appears that the two rates of left-handedness are equal. Therefore, there is not sufficient evidence to support the claim, and that should do it for this. All right, guys, that is my time for now. But I do want to keep working on this. And so if you happen to come across more questions, and let me know. I did post a new video on I did a problem from chapter 6, and I posted it in the discussion section. I'm going to show you. If you're having trouble with 7.3, I did 2 problems from 7.3. That should be enough to get you through that whole section. I did some problems from 6.4 to 6.5. Those problems should be enough to get you through the section. And we're going to save section 10. 10.3 is not going to be on the final. We're skipping 10.3, and there might be a 10.3 question on the practice final, but guess what? That will be off of the practice final and off of the real final. It will not count at all. You guys have a great weekend, and it looks like our weekend is just getting started, right? It is Saturday. So have a good one, and I will talk to you guys soon. Bye.